Here we'll revisit a problem we looked at in section 1 when we were looking at partial fractions and then using them to do an inverse Laplace transform, but we're going to see how Mathematica can do these different functions for us in a much quicker manner. So we have our big f of s here, and what we did by hand was, in order to get to f of t, we tried to do a partial fraction expansion, and it did work because we have these factorable denominator, and then each of those fractions that we split it up into does appear on the inverse Laplace transform table, so we can do the inverse Laplace transform and get our f of t. Let's see how we can handle this in Mathematica. In Mathematica, we have this basic math input palette that you're going to want to probably have running when you're using Mathematica. It may not be up for you automatically, but if you go into palettes, and then other, and then basic math input, this one's really helpful for doing radical signs or fractions or other things that we see on this list. So make sure the basic math input palette is up. Because what we can do is we can click up here, and this is going to make a fraction for us. So visually, it's a lot more easy to look at what we're trying to do. And I'm going to put in this fraction. So 2 over s squared minus 2s minus 3. Okay, so first thing I want to do, actually this step, if we're using Mathematica, is actually kind of optional because we could just do the inverse Laplace transform of this. It's going to know what we want to do. But I'll go step by step like we would do if we were doing it by hand. So I can use the apart function in Mathematica, and basically apart is going to do the partial fraction expansion for us. So if I do that, we see that immediately it's split up into these two fractions and it's automatically found the numerators for us. So if we go back to when we did it by hand, we got a negative 1/2 over the s plus 1 term, and then the positive 1/2 over the s minus 3 term. A thing I don't love about Mathematica is how it presents these, when we have variables, it's usually doing it in ascending powers of, let's say, s here instead of descending powers of s like we would normally write it, like I wrote it over here. I don't know if there's a way to change that or not by default, but when we write it out by hand, we would probably rewrite this as s minus 3 and s plus 1 instead of the way it's presenting it here. So not the best feature in Mathematica, but we'll live with it. Now we can do the inverse Laplace transform, which, not surprisingly, is called inverse Laplace transform in Mathematica. The capitalization, though, does matter. The I, the L, the T are all uppercase here. And then the thing that we want to do the inverse Laplace transform of. So the nice thing is I can just copy and paste this solution into this input here, and it's going to preserve the formatting. When we use the inverse Laplace transform function, we then have to tell it what domain are we going from. In this case, the s. It doesn't assume it's s necessarily. We have to tell it we're going from the s domain and we're going into a time domain that we're going to call t. So now it knows what we're calling the frequency domain and what the time domain is going to be called. And we can end it and run it. And we see that here we get our solution. Now, it did write in not the greatest way. Again, that's kind of a quirk of Mathematica, is sometimes it gives you a really weird form for your answer. So let me try distributing this to see if it gives it a better form. Okay, and this is a better form for us, and this is what we got when we did it by hand, is this negative e to the negative t over 2, or a 1/2 out in front, plus 1/2 e to the 3t. And this is how we would want to write as our final answer. Let me go back to how it was writing it. This is a weird way to represent it. It factored out an e to the negative t, which maybe there's a reason we would want it that way, but this is a lot more intuitive way of having our solution. Now, I could put in just that original function, and it should probably be able to do it directly without having to separate it into partial fractions. And we see that actually it can do it directly as well. Sometimes it's going to have problems doing that because it's not going to kind of figure out that it could have done a partial fraction, but usually it's pretty good about understanding those types of things and figuring out how to do the inverse Laplace transform. For this course, we will probably likely not be using inverse Laplace transform. in Mathematica that much, because we're going to see in a couple of sections that typically we're going to be staying in the frequency domain when we are doing our analysis rather than coming back into the time domain. But there are built-in functions that are able to do things that we were already doing in section 1 by hand.